Morning, my name is Mrs. Chiverton and I'm one of the science directors, and I'm going to be taking you through a series of lessons on the C3 unit about quantitative chemistry. For today's session, before we start, can you make sure that any notifications are switched off on the device that you are listening and any other devices around you? Can you also make sure you've got some paper or your exercise book and a pen, pencil and ruler in order to complete these? You're also, for this section, going to need access to a calculator. If you don't have your calculator at home with you, then you usually will find a calculator app on a phone and on any computer devices, and you can always pause the video in order to use the calculator. For this section, you will also need your planner, and if you turn to page 147 in your planner, you will find a periodic table, and you are going to need that to look up the atomic masses of some of the substances as we go through this unit. So this is just a little bit of a starter to get our minds thinking about basic arithmetic and maths. So I'm going to give you 30 seconds to complete this pre-starter and then we'll move on to the main body of the lesson. Okay, so although these are written flasks, it's basically just a maths problem. If we add 5 and 5 together, we should have come up with 10 grams. If we add 1 and 8 together, we should have come up with 9 grams. If we have 5 grams and we add something to it and the total is 8 grams, then you should have done some simple arithmetic, 8 minus 5 to give you the answer of 3 grams. And similarly, if you have 9 grams and you're adding something to it and the total grams comes out as 20, then you should have done a simple sum, 20 minus 9, and that would leave you with 11 grams. And that leads us into what today's lesson is actually about. So we're going to look at conservation of mass and relative formula mass. So our challenge today is to be able to describe what conservation of mass is and link this to balancing equations. And our aspire is to be able to actually calculate the relative formula mass of individual compounds. So we've got a starter, again, just a bit of a recall from previous lessons that you have done. So what are the 3 subatomic particles called? Which 2 particles, which are found in the nucleus, have a mass of 1? And I'm going to give you 30 seconds to think about that and record your answers in your book. Okay, hopefully you have remembered that the 3 subatomic particles are protons, neutrons and electrons, those particles that make up atoms. And of those, the 2 that are found in the nucleus that both have a mass of 1 are your protons and your neutrons. So how did we work out the answers to the starter and what rule can we come up with from this? So when we look at everything, whatever is in the first 2 flasks, when we join them together, we end up with those in the final flask. So what we can think of is that the total mass of the reactants, what we start with in a chemical reaction, will always equal the total mass of the products in that reaction. And it doesn't matter if you've got several reactants and several products, it will still follow that same rule. Mass is not created or destroyed in a reaction. Whatever atoms we have at the beginning, we have to have them at the end. They've just been rearranged. And so this is called the law of conservation of mass. You might want to make a note of that in your exercise book. So, as I've said, this happens because atoms cannot be created or destroyed. In a chemical reaction, all you are doing is rearranging the atoms from where they were in the beginning. So if we start off, in this case, with 4 white atoms and 2 red atoms, then when they react together, they could be rearranged so that they're joined in groups of 1 red and 2 white. But we still have the same total number of red atoms and white atoms. So this means you absolutely have to have the same number of atoms before and after the reaction. So in other words, on both sides of the arrow, because the arrow indicates that a reaction has happened. So looking at that picture above, as we've said, these chemicals are actually representing oxygen and hydrogen, and then the molecules of water at the end. So we have got oxygen atoms represented in red and hydrogen atoms represented in white. So in this situation, we have got 2 oxygen atoms, 2 red circles on the reactants. We've got 4 hydrogen in the reactants. And when we produce the water molecules, although they've been rearranged and joined in different ways, we still have 2 red oxygen atoms and 4 white hydrogen atoms. Same number of atoms, they have just been rearranged. So please can you record what the law of conservation of mass is and use an example as well in your exercise book or on your paper. And I'm going to give you 2 minutes to record those examples down. So you should have described in your own words what the law of conservation of mass is, and you should hopefully have used an example to illustrate. Just check your answer. Have you stated that mass is not created or destroyed in a reaction? Have you talked about them only being rearranged, the atoms? And have you mentioned that the total mass of the reactants is always equal to the total mass of products in any reaction? And given that example that we used already about the oxygen and the hydrogen reacting to produce water, please add anything on to your answer that you need to. If you need a little bit more time, simply pause the video. So I'm going to move, and we have basically achieved part of our first challenge objective there. So when we look at compounds, they have formula, and they show both the type and the number of atoms that they are made up from. So it's three very common chemicals that you'll come across a lot in your GCSE science. Methane, the gas that we burn in our Bunsen burners. Methane has this as its chemical structure, and its formula is CH4. And what that means is that there is one carbon atom, as you can see in the structure, joined onto 4 hydrogen atoms. So its formula is CH4. The little 4 simply refers to the number of hydrogen atoms. The carbon doesn't have a number attached to it, so that means there's only one. Carbon dioxide, most of you know that the formula for carbon dioxide is CO2. One carbon atom attached to 2 oxygen atoms. And with water, again, H2O, 2 hydrogen atoms attached to 1 oxygen atom. So the subscript number shows the multiples of the previous atom only, not any other ones. If, however, you've got more than one molecule of a substance, you can use a big number in front of that formula to indicate this. You apply multiples of all of the atoms by that number. So for example, this is one water molecule. Single formula is H2O. But if I have 2 water molecules, then what I would need to do is put a big number 2 in front of that. And you can see there, if you count them up, we've now got 4 hydrogen atoms. 2 times 2 is 4. And 2 oxygen atoms. 2 times 1 is 2. Hence the formula 2H2O. If I change that into 4 water molecules, then we simply multiply it up by the number of molecules that are there. So in this situation, it would be 4H2O. 4 times 2 is 8 hydrogen atoms. 4 times 1 is 4 oxygen atoms. Okay, what I want you to do is to look at these formula, and I want you to decide how many atoms of each element there are in these situations. You'll need to use your periodic table to identify some of the elements. Remember, if it's a lowercase letter, that's part of the formula of a previous element. So Ca is actually calcium, C, because it's a capital C, lowercase a. For the extra challenge ones, if you get that far, there are some brackets in there, and the clue that I'm giving you is to think about what brackets mean in maths, and that might help you to work this out. So you've got 3 minutes to get as many of these done as you can, if my timer will cooperate. Okay, so hopefully you've got through several of those, including some from the extra challenge. Let's just have a quick look at the answers. How well did you do? And please feel free to mark them as we go along. So the first one should have been 2 hydrogens and 1 oxygen. Very straightforward. All right, the subscript, remember, only applies to the atom before it. The second one was 1 carbon and 2 oxygens. Number 3, 1 calcium, 1 carbon and 3 oxygens. Number 4, 4 hydrogens and 2 oxygens. Okay, and again, the subscript again is only to the atom before it, but if you have got a big balancing number at the beginning, you need to multiply everything up as we've stated. 5 was 2 hydrogens and 2 oxygens. Number 6 was 3 sodium, 3 oxygen and 3 hydrogen. And then for our extra ones, you should have had 1 calcium, 2 oxygen and 2 hydrogen. What we've done there is we've doubled both of the atoms that are within the brackets, calcium hydroxide. For number 8, we've got 2 magnesium and 4 chlorine. And for number 9, 3 aluminium, 9 oxygen and 9 hydrogen. Again, we have multiplied up by what's in the brackets and by our big balancing numbers. So hopefully you've got most of those right. And if not, you can always go back and look at the video again and see where you have made some errors. Okay. So when we balance equations, a symbol equation is simply a way of displaying a chemical reaction using chemical symbols. It saves us writing out lots of great big names, and it also tells us what atoms are involved in that. So it must obey the law of conservation of mass. So when we balance an equation, you must add up all of the atoms of each type on either side of the arrow. And we can think about it in this example. So that was the example that we looked at beforehand. If we have hydrogen gas, which is made of 2 hydrogen atoms, and oxygen gas, which is made of 2 oxygen atoms, and we produce water, there would only be 2 hydrogen and 1 oxygen atom in a single water molecule. So there's not enough oxygen atoms. So that is not a balanced equation. All right, so if we do, all we can do is add multiples of whole molecules. We can't add odd atoms because that would change what the chemical actually was. So if we make it up to having 2 oxygen atoms, we'd have to do that by adding a whole extra water molecule. But again, that's still not balanced. So we might have to then look at the other side because we actually need 4 hydrogen atoms on the other side to give us our 2 water molecules. So therefore, what we would need to do is we would have to start off with 2 molecules of hydrogen, in other words 4 hydrogen atoms, in order to balance that. So it's quite often a process of working through and doing things to both sides of our equation. But the rules we have to remember is we can never change a formula when we're balancing the equation. You can only put a number in front of a formula to show that there's another molecule of that compound. All right, so let's consider how to show 2 molecules of carbon dioxide. That isn't right. That's no good. That's no good either. What we would have to do is this in order to show that it's 2 molecules of carbon dioxide. So we would need to look carefully when we were balancing our equations. All right, so the big rules are to count the atoms on each side of the arrow and then compare them. So here's our example. Carbon plus oxygen turns into carbon dioxide. Now this one's nice and simple. On this side, we've got 1 carbon atom and 2 oxygen atoms in our reactants. On the other side of our arrow, in our products, we've also got 1 carbon atom and 2 oxygen atoms. So that at the moment is a balanced equation. It's obeyed the law of conservation of mass. So it is balanced. We've got another example here. I've got 2 hydrogen and H2 plus N2 turning into ammonia. Okay, so hydrogen gas plus nitrogen gas turning into ammonia. If we do the process again, on the the left-hand side, in the reactants, we've got 2 nitrogen atoms and 2 hydrogen atoms. On the product side, the right side, we've got 1 nitrogen and 3 hydrogen atoms. Is it balanced? No, at this point it isn't. And you would have to put large numbers in front of some of those molecules in order to balance it. Let's put that little bit of knowledge to the test. What I've got here on the left-hand side of the page, we have got a series of reactants. On the right-hand side of the page, we've got a series of products. And what you need to do is to match the reactant with the correct product to produce 4 balanced equations. So what you need to do is count up the total number of each element in the reactants to match with the same number in the products. And I'm going to give you a minute and a half to look and have a go at those. Okay, let's check those off then. So this is what you should have got. All right, again, by counting up the number of atoms. So the first one, 2 carbon atoms, 6 hydrogen atoms, and that great amount of oxygen atoms. So that's where we end up. So we have got 3 times 2 is 6 plus 1 is 7. If we go over to the other side, we have got, again, at the bottom there, we've got 6 hydrogen atoms, 3 times 2. We've got 2 carbon atoms, and then we've got 2 times 2 is 4 carbon atoms, plus 3 times 1 is 7 oxygen atoms altogether. So to check those off, and hopefully you've managed to get those correct. So, first of all, when we're balancing equations, we need an equation with the correct formula in it, and you'll probably be given this in the exam question. So, for example, Mg plus O2, arrow MgO. The magnesium plus oxygen turns into magnesium oxide. Then all you do is list the atoms that are involved on each side of the arrow. So we know we've got magnesium and we've got oxygen atoms. Then we count up what's happening on each side of the arrow. So in our reactants, we've got 1 magnesium and we've got 1 magnesium in our products. And the oxygens, we've got 2 on our reactants. We've only got 1 in our products. So that one currently isn't balanced. And what we do then is we add big numbers to make up for the shortages. So I need 2 oxygen atoms on my products. So the only thing I can do there is to add a big number 2. That gives me the correct number in my oxygen, but it also changes the magnesium there because that big number refers to everything in that molecule. All right, so we're fine with the oxygens now, but suddenly our magnesium isn't balanced. So what we need to do then is look at our reactants and see if there's anything else that it's doing. So we're going to add another big number in this situation to try and balance up the magnesium atoms. And we'll pop that one in there. And we adjust the totals again. And then we find out that now we have the correct number of each one on both sides. So therefore we now have a balanced equation. Well done. So that's one possible method. The other way is to actually draw out atoms. So you could represent them as different coloured circles or as shaded in circles to allow you to actually balance it. But it's exactly the same principle. We're then counting up the number of each circle on each side to work out what's going on. And then we will need to add additional ones if we can, and then put the balancing numbers in accordingly, and then look on the other side and put the balancing numbers in accordingly, and then we get to the point where we have got a balanced equation. And then this final method is to do it as a grid formula with left and right. And again, exactly the same principle. So we count up the number of atoms of each type on the left-hand side and the right-hand side. We put big numbers in order to balance things. We check, we look again. If it's still not balanced, we look at the other side of the equation. Is there something different we need to do there? And in this case, there is. So now we end up with a balanced equation. So there are 3 different methods. Okay, so these equations will all need balancing. And if you work your way through the initial 4, there are some extra ones there that are a little bit more challenging for you to carry on and have a go at. So you've got the remaining of the 3-minute timer there to try and balance as many of those equations as you can. If you found one method successful, you can always try one of the other methods with the other equations to find out which one works best for you. Okay, so you can self-assess those initial 4. If you've got those correct and you want to move on, that's absolutely fine. If not, you can rewind the video, re-look at the methods that I suggested and see where perhaps you went wrong. And they're the extension ones as well. So again, mark those ones. And again, if you got any of them wrong, feel free to rewind the video, look at the instructions again and see what else you can do. Hopefully though, you've all managed to successfully balance some equations. So what we're going to do is we're going to move on. So we've completed 2 of our learning outcomes. We can describe conservation of mass and we know how to balance equations, linking those 2 things together. So now we're going to look at being able to calculate the formula mass of some compounds. So the relative formula mass is relatively easy. We need to be using the periodic table in our planner. All right, we're going to choose one element and we're going to write out its symbol, its atomic number and its mass number. And then what I want you to do is to tell me what each of these numbers can tell us about the element. And I want you to give me as much detail as possible. You can choose any element, but I've put helium up there for those of you who don't have access to a periodic table at the moment. So in your 1 minute, look up your element, write down its symbol, write down its atomic mass and number, and tell me what each of those numbers tells us about that element. So if we use my example of helium, we should have written down the symbol, which is the He. We should have had two numbers, 4 and 2. So the letters are the symbol element, as you well know, and the number at the bottom, the smaller of the two numbers, is the atomic number, and that is equal to the number of protons. That's one piece of information that number can give us. And that also, in an atom, equals the number of electrons as well. The second number at the top is the mass number. It's the massive number, is the way that I remember it. And that one is made up of the number of protons and the number of neutrons. Because remember, in an atom, the subatomic particles that have enough mass for us to worry about are the protons and the neutrons. So, as I've said, we remember the mass number as the massive one. All right, and it's also referred to as the relative atomic mass because it's comparing different atoms with each other. And we can use a symbol, capital A, with a subscript R to represent that because us lazy chemists don't like writing out relative atomic mass all the time. So again, using your periodic table and just a bit of practice, I'm going to give you a minute to look up and write down the atomic masses of each of these elements. So just write down the name of the element and next to it pop down its relative atomic mass. Excellent. So remember that it's the massive number that you should have been looking for. The most common mistake is that people look up the smaller of the two numbers, the proton. So very quickly, you should be able to just self-assess your answers and check you're working off. As I say, if the number is much lower than that, you've either looked at the wrong element or more likely you've looked up the atomic number rather than the atomic mass number. So when we talk about the relative atomic mass, it is the massive number, and we can look them up in the periodic table. But there is another term that's used regularly in chemistry, which is the relative formula mass. And again, it has an abbreviation, capital M with a subscript R next to it. And what it is the mass of all of the atoms in the compound combined together. So for example, magnesium chloride, we know, is made of a magnesium atom and 2 chlorine atoms, chemically bonded together. And what we would do in order to find out the mass of them, the mass of the magnesium is 24, the mass of the chlorine is 35.5, but remembering we've got 2 of those, so we simply add those masses together and that will give us the relative formula mass of any compound. In this case, we've got 24 plus 35.2 times 2, making it 71, add those 2 together and we get the 95. This is often the starting point of lots of more complex calculations, but it can be simply worth 1 or 2 marks just in its own, either in a calculation or as a separate question. So we need to be able to practice and do this. So over the next few lessons, you are going to use relative formula mass quite a lot, but we just need to remember that. I've given you the atomic masses of each of the elements that are involved in these particular compounds. And what you also need to do is remember what those brackets meant when we were looking at formula. So again, what I would like you to do is, looking at these, we're going to do one example together. So ammonia, its formula is NH3. So that tells me there is 1 nitrogen atom and 3 hydrogen atoms because the subscript number is after the 3. So therefore, if we want to work out its relative formula mass, we look at the atomic masses of those individual atoms. So we need 14 plus 3 lots of 1 because there are 3 hydrogen atoms, each worth 1, and we add that together, it comes to a total of 17. If we look at sodium, we've got 2 lots of sodium, 2 times 23 plus 16, and it comes to a total of 62. With the magnesium one, we've got a magnesium atom, and then we've got the OH in brackets 2. That means there is an oxygen and a hydrogen atom, but we have that twice. So we need the 24 for the magnesium, and then the 2 lots of 16 plus 1, 16 for the oxygen, 1 for the hydrogen, added together, and in total that comes to 58. And similarly with our calcium nitrate there, we have the calcium, which is worth 40, nitrogen on its own is 14, 3 lots of oxygen, but then we need to multiply that whole lot out by 2 as well, which gives us our 164, but it's only twice what's in the brackets. Now you can write them out as separate atoms in order to do it. You don't have to use brackets if you don't feel comfortable doing that. You just write out all of the individual masses and add them together. Either way will get you marks on the exams, but please show you're working out when you're asked to calculate the relative formula mass of a compound. So this is your turn. And I'm not asking you to do all 10 of them, but you might have time to do so. I'm asking you to pick 4. Use the periodic table to find the atomic mass of the elements involved. Challenge yourself to do at least one of the ones with brackets in it. And don't forget to show any working out of anything that you are doing. So you have 2 minutes to get 4 done. Hopefully if you managed to get at least 4 of those done. If you've done some more, that's absolutely fabulous. I'm going to put all of the answers up for you and you can self-assess what you've done. So in each case, what we've got there is the working out and then the final answer for that sum. So I'll just leave those up for just a moment. Again, if there's anything that you've done wrong, just look back at the working out that I've given here and you hopefully will see where your error actually is. So when we look at calculating our relative formula mass, we can look back at how we balanced equations earlier on. So we had 2 molecules of hydrogen plus a molecule of oxygen making 2 molecules of water. And if we wanted to calculate the total molecular mass of the reactants and the products, you should see something. So if we add up, we have got 2 lots of 2 for our hydrogen plus 2 lots of 16 gives us a total of 36. And when we look on the other side of the equation, for our water, we've got 1 plus 1 plus 16 for a molecule of water, but we have 2 of those, so we double it, and lo and behold, the same answer appears. So when we look at the total molecular mass of the reactants with the total molecular mass of the products, in a balanced equation, the 2 values will be equal. So the molecular mass of the reactants will equal the total molecular mass of the product if the equation is balanced. And that is, of course, because of this idea of conservation of mass. Because whatever atoms appear on one side, and they're the things that have the mass, they have to appear on the other side. Okay, because it's so important, I really want you to practice this a little bit more. So this is some independent work that you should be doing. So in each case, you're going to work out the relative formula mass of a particular compound and you're going to show your working out every single time. So we've got magnesium oxide, we've got sulfuric acid, we've got zinc chloride, and we've got lithium chloride. Put an extra challenge in for some of you there. You need to find out what the formula for lithium chloride is. Lithium is in group 1 and chlorine is in group 7. So that should give you a clue, if you think back to your bonding information, what the formula would be. And I'm going to give you, again, about a minute to actually complete those relative formula masses. Okay, so magnesium oxide, very straightforward. We should have 24 plus 16 equaling 40. With our sulfuric acid, 2 lots of hydrogen, 1 plus 1, a sulfur at 23, and 16 times 4 for our 4 oxygens comes out as 98. Zinc chloride, 65 for the zinc, 2 lots of 35.5 for the chlorine, 136. Lithium chloride, if lithium is in group 1, it makes a +1 ion, and chloride is in group 7, so it makes a -1 ion. So therefore the formula for lithium chloride is simply LiCl. Therefore, when we look at its molecular mass, it's simply 7 plus 35.5 comes out as 32.5. And hopefully if you've managed to get those sorted. So how do we apply this to an exam question? This is a typical one. And again, it's using compounds that you may not have heard of before. Titanium chloride, you've heard of sodium, and I hope you've heard of sodium chloride. This is just looking at this idea of conservation of mass. Remember what we said, that the mass of the reactants equals the mass of the products. It's asking you to do a calculation. So what you should do first of all is annotate the equation with what you actually know. So there's lots of information in that question and lots of numbers. Okay, check the units because sometimes they do challenge you by mixing up kilograms and grams or tons. Highlight anything that's missing because that's the thing that you're going to be finding out, and then rearrange to find your unknown answer. So in this question, we know how much titanium there is, so the titanium 4 chloride. So I'm going to write that answer up here. It also tells me how much sodium was involved, so I'm going to write that answer there. So if we add those two numbers together, that gets us the total mass of the reactants. Over the other side, I know what sodium chloride is. What I don't know is the titanium. That's our X value. That's what we're trying to find out. So when we convert that to an equation, it's not a complex calculation. It's just testing that you understand the law of conservation of mass. So it's simply add the two reactants together, 1140 plus 552, and that will equal the mass of the titanium, X, plus the mass of 1404, which is the mass of the sodium chloride. Simplify that down, rearrange it, and we end up with a mass of titanium of 288 kilograms. So now we are able to do that final aspire part of our challenges. So these are notes that summarise everything that you need to do. If you want to make these notes and there's anything that you have missed, please pause this video and get those learning points down into your exercise book. So the law of conservation of mass states mass is not created or destroyed in a reaction. Atoms cannot be created or destroyed, only rearranged, so the total mass of the reactants is always equal to the total mass of the products in any reaction. Compounds have formulae that show the type and number of atoms that they are made from. To calculate the relative formula mass, we simply add together the atomic masses of all of the atoms shown in the formula. A symbol equation is a way of displaying a chemical reaction using chemical symbols and formulae. The symbol equations must obey the law of conservation of mass, so to balance an equation you must have equal amounts of each type of atom on either side of the arrow. You may need to add molecules to each side in order to get an equation to balance. You can never change a formula when balancing an equation. You can only put a number in front of a formula to increase the number of molecules. If you have more than one molecule of a substance, you use a big number in front of that one to indicate this, and you multiply all of the atoms by that number. At the end of this lesson, please complete the Google quiz. It's multiple choice questions and therefore will be marked automatically so you can get some instant feedback. If you get anything wrong, there is feedback for those wrong answers. Thank you for listening. This is an extra exam question that you can have a go at.